In this video, we continue our investigation of the structure of electron clouds by looking more closely at orbital diagrams, and in particular the orbital diagram for the simplest atom hydrogen, which contains just a single electron in its electron cloud. This is the orbital energy diagram for the hydrogen atom that we were introduced to in the previous video. By now we know that electrons in atoms exist in orbitals, and in this diagram an orbital is represented by a horizontal line. It is important to remember that an orbital is simply a region of space where there is a high probability that electrons exist, if indeed the orbital is occupied by an electron. Orbitals and the electrons that reside in them have a characteristic and well-defined energy, and the distribution of electrons throughout an orbital also has a characteristic shape and orientation. And these three properties, energy, shape of electron distribution, and the orientation of electron distribution, are characterized or described by three quantum numbers. N, the principal quantum number, which describes the overall energy of an orbital and takes on the values of positive integers up to infinity. L, the secondary quantum number, sometimes called the angular momentum quantum number or the azimuthal quantum number, which describes the shape of electron distribution and takes on the values of 0, 1, 2, etc. up to n-1. You will also note that the secondary quantum numbers written across the top also have letter designations associated with them, S, P, D, and F, corresponding to L equals 0, L equals 1, L equals 2, and L equals 3, respectively. The third quantum number, ML, is the magnetic quantum number, which in this diagram is represented by numbers underneath the horizontal lines, and ML describes the orientation of electron distribution in space and takes on values of -L up to +L. Orbitals exist in subshells, which have differing numbers of orbitals in them according to the value of L. And subshells exist in shells, namely the n equals 1 shell, n equals 2 shell, n equals 3 shell, etc. The subshell designations, for example, for the 2p subshell, is determined by the shell number that the subshell resides in and the letter designation corresponding to the relevant L value. So in this case, the subshell designation is 2p. Similarly, for the 3D subshell, its orbitals lie in the n equals 3 shell, and they have a secondary quantum number of L equals 2, corresponding to the letter designation of D, hence the 3D designation. As I said, this is the orbital diagram for the hydrogen atom, which contains a single electron, and that electron can be represented using an arrow placed on one of the horizontal lines, indicating that the electron resides in or occupies an orbital. And typically at room temperature, the single electron would reside in the lowest n equals 1 energy level. However, if we heat up hydrogen atoms and excite the electrons in them, we can promote the electrons to higher energy levels, and it is possible that they can go to any number of orbitals in any number of subshells and shells. And when electrons exist in different orbitals, subshells, or shells, the properties of the electron cloud changes. And it would be good if we were able to describe the properties of electrons in those different orbitals. For example, how would we describe the properties of an electron that sit in an orbital of the 2s subshell? First, we can recognize that the shape of the electron distribution around the nucleus is spherical, since all s orbitals have a spherical distribution. Second, we can recognize that the 2s electron is in the n equals 2 energy level and is not at the lowest energy level. It is not at the ground state energy level, but nor is it at a high energy level. So in summary, we can say that the electron of the hydrogen atom represented by this orbital diagram is spherically distributed around the nucleus, has moderate energy, and exists on average at moderate distances from the nucleus. Let's now consider the characteristics of the electron if it happened to exist in one of the p orbitals. Then the shape of the electron distribution would be dumbbell shaped, and it would take on one of these three orientations. And the electron we have shown on the screen happens to be in the 2p-1 orbital, which is the orbital shown on the left, and where the electron distribution is oriented along the x-axis from the perspective of the observer. Since this electron exists in the n equals 2 energy level, we would again say that the electron has moderate energy, exists on average at moderate distances from the nucleus, and is distributed around the nucleus in a dumbbell shape oriented along the x-axis. And so what we're seeing here is that a combination of the relevant quantum numbers and the pictorial representation of the orbital diagram now allows us to describe some of the relevant properties of electrons within electron clouds, no matter which orbital they reside in. If the electron in a hydrogen atom were promoted up into an orbital within a d subshell, then the distribution of the electron around the nucleus would take on one of these 5 orientations, and in this case we can see that the electron is actually sitting in the 3d-2 orbital, and that's the one that's represented on the bottom left hand side. So we would now say that the electron is distributed in a double dumbbell shape around the nucleus, oriented along both the x and y axes, has relatively high energy, and exists at relatively large distances from the nucleus. Finally, if the electron happened to reside in an f orbital within an f subshell, then its distribution would take on one of these 7 orientations, and we can see that the electron happens to be sitting in the 4f-3 orbital, which again is represented on the bottom left of these 7 possible orientations. So we would say that this electron is distributed around the nucleus in a quadruple dumbbell shape oriented between each of the x, y, and z axes. The electron would be said to have high energy and would exist on average a large distance from the nucleus. One last point to make about this orbital diagram is that we have noted how useful it is in terms of identifying the 3 quantum numbers that characterize an orbital. For example, we can identify the 3 quantum numbers for the electron occupying this orbital by noting it sits in the 4th shell, which gives a principal quantum number of n equals 4, and this gives us information about the energy of the electron and the relative distance it lies from the nucleus. It sits in an f subshell, which means it has a secondary quantum number of L equals 3, which tells us about the shape of the distribution of that electron around the nucleus, and it specifically sits in the 4f-3 orbital, which gives us information about the orientation of the electron distribution. And it was the information garnered from these 3 quantum numbers that allowed us to describe the properties of this electron and ultimately the entire electron cloud, which we will see later on allows us to predict chemical properties such as how atoms will bond with each other.